Yes, sir.
I have a question regarding the lab.
Okay.
Did you throw a curveball in there by any chance?
What do you mean?
On tone 5?
Oh, with getting 0?
No, well, no. What happened was, because basically my strategy was I isolated each tone and then just found the frequency content that's specific.
Okay.
And for all of them, I get a high frequency and a low frequency, and they can be very distinguished. Well, for tone 5, I got 2 high frequencies. And
You talking about the computer assignment?
Yeah.
Oh. You got 2 frequencies. Oh, well, okay, so.
I got 2 high, 2 low, but the 1 high doesn't correspond to anything.
Yeah. I didn't throw you a curveball, but, all I did was I hit record on my desktop and I put the phone on speakerphone and I dialed the number. Like, I wasn't purposely trying to throw it. But having said that, there are some real-world limitations of creating cosines that you might want to think about. So, the brief advice would be, if you see frequencies that correspond to the ones that you're looking for, those are your frequencies. There may be other frequencies as well, and when I said if you notice other things, you should discuss them, that would be something that you can discuss.
Okay.
I saw other frequencies, and then maybe you can see if there's a pattern. Like, do those frequencies correspond to anything? I'll be willing to bet that they're not random, those other frequencies, that they have something to do with something, and that has something to do with something that you've learned in this class. Okay.
Really?
Yes. That you already know.
Did you factor in when you record, the noise factor in that process of recording from the PC?
What do you mean by the noise factor?
Well, because you're recording in the phone.
There's noise, yes.
Yeah. So
Yeah.
could you make that assumption that it could be related to the noise?
Oh, there's noise there, but noise is not going to give you, so white noise, as we're going to learn about, is like sort of noise that's distributed over all frequencies. And it's kind of a low-level background thing. So you'll see that across all frequencies. But if you're seeing a big spike, that ain't noise. Right? That is real, but, and it is somehow derived from the tones that are being created. You just might want to think a little bit about where that may have come from. Think about your first assignment. Yeah?
Right. Well, let me ask you this. Let's just say we isolate the 1 tone, and then we do a frequency plot. We get 2 high frequencies that do correspond to the chart, and 2 low frequencies that correspond to the chart. Could we assume that 2 buttons are being pressed at the same time?
That was never the case.
Is there like an on button that has a different tone or something?
Nope, I just pushed digits 1 through 9. Did I get all of them? No, let's see, I didn't do that one. No.
Got the numbers.
I didn't do 4. Just 4. 4 is the only one that's not there.
Could it be your phone number, your cell phone number?
No, I wouldn't call that number. All right. So I don't think it rings to anything. There is a relevance to the number, though. If anybody can figure out the relevance to the number, I'd get a kick out of it.
Call it taxi.
Call it taxi.
It opens a black hole on Broad Street.
Yes, it opens up. I don't think that takes much these days. Okay, so some sort of hotline. So in case I'm sure everybody's seen it, but I mean basically what it is I recorded. This is computer assignment 2, due in a couple weeks. I'm going to give you some code today that will help you. Actually, that code is already on Blackboard under the lectures section. But basically, I turned on the mic on my desktop. I dialed the phone number. That's it. You're getting that recording. Your job is to tell me what phone number I dialed. And the tool you have is that it just so happens that there's this matrix. Like every time you push a button on your phone, you get 2 frequencies at the same time. So there's like a grid. It's like, so different combinations of frequencies give you different numbers. But it's always 2 frequencies. So basically what you got to do is you've got to use your computer Fourier analysis skills that you're going to learn today to look at those frequencies and say, hey, I see frequencies, he must have dialed this number. I see frequencies, he must have dialed that number. And then tell me what the phone number was. It's kind of a cool assignment. So we'll see if it works. I've not given this assignment before. Usually I recycle a lot of assignments. This one I have not recycled. I just wrote it 2 days ago.
Wasn't that process a huge advancement when they made telephones? Like before that, didn't they have to switch manually the numbers that you would get to switch
No, before, I mean, that's tone. Before that, they had it with, like, where you dial it, like where you wrote the rotary phones, and I don't really know what that system was based off of, but it wasn't frequencies.
Okay.
So yeah, but I mean, that technology is. Yeah, I'm not like, talk to Dr. Szilagyi. He knows this stuff inside and out. I'm sure you could find it on Wikipedia. I'm just not real familiar with it off the top of my head. But yeah, it's certainly not a new technology. I mean, it's existed since I was a kid. I'm old. Okay, questions about the exam? I do have to say this. I think it's one of the easier ones I've given. I think you guys got off pretty easy. So you can expect fire and brimstone for the second exam. Because I have a reputation to maintain. You know. Okay, so having said that, let's talk more about Fourier transforms. And I do want to get to this, I've got something in mind that I want to get through today, because at the end, sort of about half of your class, I want to switch to MATLAB, and I want to show you some of the code that you're going to be needing for this assignment. So that's why I'm really kind of pushing to get to it. So on Monday, we did this example where we took a rectangular pulse. Is that right? Monday? Oh, right, because Monday was review, wasn't it? Okay, right. Good grief. Okay, so we did this thing where we looked at the frequency content of a rectangular pulse, and I think when we did the frequency content, we did it in terms of we put specific numbers, like for the height and the width and whatnot. Is that right?
A and B.
Oh, we did A and 1 over 2A? Oh, we did that. Okay, great. Okay. Yeah, we did it right from the textbook. Okay, so just to okay, so good. We were better off than I thought. Okay, so we did this. The area was always 1. Is that right? Okay, so area equals 1. And we wrote the integral. So we said that the Fourier transform was the integral from minus a to a of 1 over 2a e to the minus j omega t dt. And we integrated that, and what do we get? Sine of a omega over a omega. Okay. And I said this had a special name called the sinc function. And it has a very distinctive shape that you're going to see over and over again. If you were to plot the frequency content of this signal, magnitude, right now we're just looking at the magnitude. What you get is something that looks like such. Now this shouldn't surprise us, right? Because what we've got is a sine, but then that sine is divided by omega. So as omega gets bigger, you're dividing that sine by bigger and bigger values. So it's like a sine whose amplitude, whose height gets smaller and smaller and smaller as omega gets bigger and bigger. So that's kind of expected. What's the value at omega equals 0? Ooh, DC offset. That's good. Can I actually calculate a number? What is the DC offset of my signal?
1, the area under the curve divided by.
Right. Well, because it's an aperiodic signal, you don't have to divide by the period because there is no period.
1 over 2.
Right. There's no period. There's no period. Right. For an aperiodic signal, it's the same thing. You're going to remember before we integrated over one period and divided by the period. Now there's no period. You just integrate over all time. So what's the area under the curve? I mean, that's what this is, right? That's just the area under the curve. What is the area under the curve? 1. It says it right there. Look at that. Right? Wow. Okay, 1. Is that what this equation predicts? If I put omega equals 0, I get sine of 0 over 0. Is that 1? Yeah, hit it with L'Hopital's rule.
Actually, it's not L'Hopital.
No, it is L'Hopital's rule, because if you let omega equal 0, you get sine of 0 over 0. So that's L'Hopital's rule. So you take derivative of numerator and denominator. Derivative of the numerator gives you...
Negative cosine.
no, not just cosine. A cosine A omega over A. Thank you, calculus students. Okay, that was awful. Good. Right, so I presume everybody remembers how to take the derivative of a sinusoid, how to apply the chain rule. You know, you need to know that kind of stuff. Okay, so we took derivative of numerator, derivative of denominator. Look what happens to the A's. They cancel. That's awesome. And if you let omega equal 0, you get? 1. As advertised. So yay, it all works out. Okay? Good. Okay. Yes? Yes?
Why did we put that half up and half below the signal?
I'm glad you asked. Okay.
Because that, wouldn't that make that 0 and then couldn't really think of
Okay, so that's a great question. So let's talk about some variations on this now and see if we can apply some logic to this. So what if I gave you that? And said find its Fourier transform. Let's put some numbers here. I mean, let's say that this is still minus A,
The magnitude wouldn't change.
A,
DC offset.
and this height is still 1 over 2A. But we'll say it's like even across the axis.
So just like the Fourier series, the magnitude of your Fourier.
Magnitude doesn't change. What's the only thing that's different?
DC offset.
DC offset. And DC offset is energy at what frequency?
0.
0. So how is my plot going to change? It's going to go down by how much?
By 1.
Right. It went, well, how many units did it go down? It depends on the value of A, right? If the whole thing is 1 over 2A, it went down by half of that, right? So 1 over 4A. So what you would do in that situation is you would do 1, you draw, basically just draw, there'd be like a discontinuity here, and this would be 1 minus 1 over 4A. Yes?
You have to account for it because now you're just looking at the positive area now. If you move the entire signal down.
You can't integrate it anymore, right? So what you do in that case, if memory serves me correctly, and God knows it may not, I think what you do in that case, so the question is, if you want to just come and look at this and solve for your Fourier transform at omega equals 0, your DC offset, you can't just apply that integral because this thing integrates to negative infinity, right? So what do? So in situations like this where you can't actually do that, no. Well, you could either shift it up, integrate it, and then shift it down, right? Which is basically how we figured that answer out. Or what you do is you pretend that there's a period. Solve for omega 0, pretending there was a period, and then you let your period go to infinity. So in this case, if we pretended that this was a periodic signal with period t, what would be your DC offset? Right? It would be 1 over t times the area under the curve. What is my area under the curve? Well, first you'd have this area, and then you'd have this area, and then you'd have that area. Let's try this real quick and see if it works. I hope it does, because I haven't done this at home. I don't know if this is actually going to work, but I think this is how you do it. Okay, well, what is this area?
1 over 2A times A minus A minus 1/2.
Right, so first of all, this is minus 1 over 4A, and this is 1 over 4A, right? It's half of that height.
It should be just 0.5 by the definition of A equals 1 over there.
A equals what now?
A equals 1 in the original signal that we were looking at. So
Big A equals 1, the whole area.
yeah, so all those areas under those three sections should each be 0.5.
But you have, I don't think.
No, it depends how far-
Negative Q or 2 is the same distance as A to
Yeah.
Okay, never mind. Sorry.
No, it's a good guess. Okay, well, let's start with this area. This first area here is T over 2 minus A times minus 1 over 4A. That's this area. So it's the base, which is T minus 2 over A, times the height, which is minus 1 over 4A. And times it by 2, because this and this are going to be exactly the same. Okay, and now we're going to add this rectangle, which is the base is 2A, and the height is 1 over 4A. Okay, good grief. Let's see what happens. 1 over T. Okay, that 2 gives me a 2 here. So I'm going to get minus T over 4A plus a half plus a half. So that's going to give me minus 1 over 4A plus 1 over T. You with me? Oh, this is fun. Okay. This is going to work. Yay, intuition. Okay, good. Now you let T go to infinity, because really this signal isn't periodic. So if you let T, I didn't put numbers here. I just said, well, let's just make it a period. So we found the average value over one period. Now I'm just saying, pretend that period is so big that this thing never repeats. So basically, let T go to infinity. Let the period go to infinity. What happens when you do that? And what are you left with? Minus 1 over 4A, which is exactly the amount of units that we shifted it down. Minus 1 over 4A. So it all worked out. So, two methods of getting the same answer. One was you could just eyeballed it and said, well, that's just a square function that we moved down by 1 over 4A units. Or if you're hell-bent on applying the integral, have at it. You get the right answer. Right? You just have to employ this little trick of pretending that it was periodic and then letting your period go to infinity. You still get the same answer. I don't really recommend this method, but it's just good to know that it all fits. Okay, what if I gave you this function? Let's make this hard. No calculus, please. I'm hearing a 2.5. I'm just writing down things that I hear. We're going to figure out how to put them together.
A is 2.5.
A is 0.5. 2.5.
So it should be.
Area is 15. Woo! Let's unravel this mess.
I think it'll be 15.
Supposing you forgot everything, how could you get the answer to this?
Plug and chug.
Plug and chug. Okay? Method number one. Method number one. The frequency content of this signal is equal to the integral from 0 to 5 of 3 e to the minus j omega t dt. End of discussion. Right? If I were to do that, I will get 3 over negative j omega times e to the minus j omega 5 minus 1. And I don't know, you can polish that turn a little bit and turn it into something, but that's basically the right answer. Okay? Okay, but I like intuition. I don't want you to have to integrate every time because in a minute we're going to make the computer do all the math for us, so we're really not ever going to do the integrals again. But what's valuable is the intuition, like knowing how all this goes together. So what if we do this? Instead of solving this problem, let's solve an easier problem first. What if, could we center this at 0? Okay, so if I were to center it at 0, what would it look like? Minus what to what? Good. So minus 2.5 to 2.5. And according to my original model where the area equals 1, that means that I would have to have a height of 1/5, right? So basically, if this were the problem, I would know how to get the answer, right? So let's say that was my answer. What would my answer be if this was my question? What would my frequency content be?
Sine 2.5 omega over 2.5.
Sine 2.5 omega over 2.5 omega. Plug and chug, right? We've already done that one. It's just a matter of figuring out what little a equals. Now, that's cool. Now the first problem is that this one has an area. What's the area of this rectangle?
15.
All right. Over here my area is 1. So how do I account for the fact that that area is a lot bigger? Yeah. I mean, all I have to do to take this rectangle and give it an area of 15 is to make it 15 times taller, right? Multiply it by 15. And we've already learned that Fourier transforms have the scalar property, right? If you double the input, if you double the x, you double the Fourier transform. So all I got to do to account for the area being 15 is to slap a 15 out front. Sweet. Okay. So now I have, so that expression is the Fourier transform for that function. And now I got to shift it to the right in order to get the one that was my original question. How do I do that? Right, so we've learned that when you take your original signal and shift it to the, see here we go with the minus signs again. When we shift it to the right, when we shift it by tau units, that equivalency in frequency space is to take your original Fourier transform and to multiply it by e to the j omega tau. Right. In this case, I want to take this and shift it to the right. That's a shift. So a shift to the right means you want to have tau minus 2.5. Right. Tau minus 2.5 shifts it to the right by 2.5 units. So e to the minus j omega 2.5. And we're done. No calculus. And if you gave me a few minutes, I could prove to you that this answer and this answer are exactly the same. Not kind of the same, not in the same ballpark. They are exactly the same, believe it or not. Okay?
So is it best to always start with a base condition like this, where it's easy to find the Fourier and then apply it?
I think so. It's easier because at the end of the day, what you're trying to derive out of this is a little intuition. And if you don't do this, like if you just stick with the plug and chug, you know, you're never going to, right, you're going to lose, I mean, the real value in this, I mean, when I look at this, what I see is I've got a sinc function, and I can calculate where that sinc function zeroes out. It's got some sort of amplitude associated with it. That's kind of important. And what's this expression going to do?
Time shift.
Well, it's going to give me a time shift, but when I plot this in the frequency domain, how is this going to affect the magnitude?
Not at all.
Not at all. This doesn't affect the magnitude. This part affects the magnitude. This just affects the phase part. Okay. Where does this function zero out? So if I were to plot that, if I were to plot this in versus frequency, we'll play MATLAB as soon as this is over. So if I were to do the magnitude of, what do we call it, f? So let's plot the magnitude of f of omega for this particular function. So what's it going to look like? Hold it right there. Can we agree it's going to look like a sinc function?
Yes.
It's all window dressing after that, right? So stop. Draw yourself a sinc function. Doing, doing, doing. Doing, doing, doing. The only hard part left is labeling this number, labeling that number. Top number is 15, because we know that in a regular sinc function where the area was 1, that this height was 1. But now we scaled it by a factor of 15. So that's all you got to do is put the 15 there. That makes sense, because we said the DC offset is the integral of this thing, is the area under the curve, which is 15. Therefore, at omega equals 0, you should always get 15, right? That's the area under the curve. So that's good. Now what's this frequency here?
It's going to be 2.5 times pi.
Right, so remember, this thing zeroes out when sine of 2.5 omega equals 0. Like, when this term equals 0, the whole thing equals 0. Right? That's the only way to get that function equal 0. I mean, your denominator can't make this function equal 0. The complex exponential can't make this function equal 0. The only thing that can make this function equal 0 is when the sine term goes to 0. Okay, so how do you get sine of 2.5 omega to go to 0? Right, remember sine of theta goes to 0 when theta equals 0, pi, 2 pi, and so on. So in other words, I need this term to be pi, 2 pi, 3 pi, and so on. Those are the frequencies where my sinc function will zero out. Okay, so if 2.5 omega equals pi, that means the first zero frequency is pi over 2.5 radians per second. So here we go. Whatever that number is, pi over 2.5 radians per second. Some frequency. I don't know and don't care. So that's where it zeroes out. What about the next frequency? It's double that. It's 2.5 omega equals 2 pi. So you just double everything. And these are all evenly spaced. 2 pi over 2.5, 3 pi over 2.5, and so on and so forth, off into infinity. Crazy! See? Not too bad. We can look at the frequency content, so we can look at the phase plot, and that would tell us roughly the same. It would be kind of a similar story. We can look at that in a minute. Are we all on the same page? How do we deal with the phase shift?
The phase shift, so
Let's talk about that.
by that definition, it's J omega T, right?
You J omega tau. Tau is the shift.
J omega tau is the shift. Now this tau is negative, so when you plug in with shouldn't the exponent be maybe 2.5? Does that make that
No. It's e to the j omega tau. So if you had x of t gave you x of omega, the rule says that if you then apply a shift of tau units, what you get is x of omega e to the j omega tau. Now in our case, we shifted it to the right by 2.5 units. And that happens when tau equals negative 2.5. Because remember, negative tau is always means shift to the right. So that's what we got.
So you're not going to stick the negative in there, just put the...
Right. I'm not doing negative of a negative. See, this is one of the advantages of having taught this class many times, is I've tried teaching this by saying, let's pretend the shift is t minus tau. Okay, then the rule becomes e to the minus j omega tau. And then people look at this and they're like, well, it shifted to the right. So is it tau equals minus 2.5 or 2.5? And everybody gets confused and loses the minus sign.
What's that in the other test? I literally saw it, I was like, oh.
Don't lose sleep over it. Okay. I'm actually going to hold off on the phase discussion for a moment. It's important, and we are going to talk about it. But it's kind of important to me that we first talk about the MATLAB stuff, because I want to make sure that everybody's sort of has the skills to start tackling the computer assignment over the weekend. I don't want that to fester till Monday, because then you'll lose. Well, I doubt anyone's actually going to work on it, although I wish you would. But at the very least, you'll lose your excuse. And that's as good as anything to me. Okay, so once again, they make me dive for cables. Oh, somebody changed the cable. Let's see if this one's any less ridiculous than the previous one. Okay, so because I am nice, I have taken the liberty of writing a little code to make your life a little easier. Hello. Alrighty. So, there is a well-known function. It's existed for probably 50 years, maybe longer. It's called the fast Fourier transform, FFT. It is a mathematical algorithm for taking a signal and computing its frequency content. Sound good? All right. So let's try it and see what happens. So, all right, so let's see, t equals ln space 0 to, I don't know, 10 seconds. X equals cosine 2 pi, I don't know, t, plot, let's see, subplot 2 on 1, plot tx. So here's a signal. Does everybody agree this is a 1 Hertz cosine? Say yes. Great, thank you. Okay. I've run it for 10 seconds. Signal peaks 10 times. It's a 1 Hertz cosine. Let's take the FFT and see what happens. Look how easy this is. Oops. X. So I'm going to use little x for time signals and big X for frequency signals. That's how I differentiate between them. So big X equals FFT of a little x. Let's see, whose? Okay, so let's just take, before I even try plotting it, let's just see what happened. So little x had 100,000 points in it, and they were all reals. Big X, that I just computed, also has 100,000 points in it. But look at it, now it's complex. Does that surprise anybody that it's complex? No, right? I've been sitting here for a month now telling you that when you take the frequency content, it always comes out complex. That's why you got to do magnitude and you got to do phase. Okay? So it's complex. That's fine. And it's got exactly the same number of points as the input. That's how FFT works. So it's complex. So that means we're going to plot the we got to plot either the magnitude or the phase. Let's start by plotting the magnitude. Yes, sir.
Random question. Will we need to install any more toolboxes for MATLAB over the course of this semester?
No, I don't think you should.
Okay.
Is FFT not working?
No, I was just asking.
No, FFT should be built right in. Okay, so let us go to subplots. 2, 1, 2, plot. Oh, what do I put on the x-axis?
Time? Or no, frequency domain. So it'll be 1 over t.
When I plot you're right. I mean, when I've been doing these frequency plots, after I take the FFT, and I want to do like magnitude of f of omega or whatever, what goes on this axis? Frequency. Okay, do I have that frequency vector? No. Oh, uh-oh. So that's the first.
Would you do 1 over t times 2 pi?
1 over t, 1 over which t?
Time?
1 over time times 2 pi? No, not really. That won't work. Because this is 0, like 0.01. I mean, this will give you, that won't give you frequency. Not the way you think it will. Because that's not period. Sort of. All I want you, what's that? We make an omega vector. All I want to do is just point out that we don't have a frequency vector, We need to make one if we're going to plot it. That's all I want to say. Okay, but for right now, I can actually generate the plot without creating the frequency vector. But I just want to make a mental note that I don't have one right now. Okay, FFT didn't create one for me. Yes, sir?
Isn't T just a series of numeric values equally big?
Yes?
And we can't just use that as a mega? Does it have units in it?
Well, T is units of seconds. It's time. But I want frequency.
On that graph.
On the top graph, it's numbers. I mean, I could plot it. It wouldn't give me an error, but it would be meaningless. I mean, if I plotted it versus T, then my x-axis would go from 0 to 10. But that doesn't make any sense. Like, it's not 0 hertz to 10 hertz. Just hear me out. This will make more sense in a second. I'm just going to plot the absolute value of big X. That's going to give me the magnitude. Okay, so look at what I've got. So right now my x-axis is 0 to 10 times 10 to the 4th. So all it's done is it's just plotted, if you don't give it an x-axis, it just numbers them. So the first element, the second element, all the way out to the, where am I? All the way out to the 100, see how I have 100,000 points? That's what this is. This is just indicating the 100,000th point. And what do I have? Mostly zeros, right? I mean, mostly zeros. It looks like there's a little bit of action over here at the beginning and a little action over here at the end. Let me zoom in a little bit. Ooh! What's that? A spike. What do you think that spike is? I got a sine wave. What should my frequency content be on the sine wave? A pure tone, a single frequency. What does that look like? It is a pure tone. That's a single frequency. Everything's 0 except for that 1 point. That's a frequency. Okay? What's that? Oh, let's talk about the triangle. Why does it look like a triangle?
Because your cosine is actually finite. You only define your cosine.
Even better than that. Watch this. Let me take this plot and add a marker to it.
Now it's only discrete points, so.
It's only 1 point. It just connected the dots. That's why it looks like a triangle.
So if you increase your sampling, you would see it like get narrower and
Right.
narrower.
Unfortunately, there are going to be some times where even when you put a sine wave, you're going to get more than one dot there. And we're going to talk about that because that actually turns out to be really interesting and really important.
Is that aliasing?
No.
No.
We'll get there. We'll get there. Aliasing is cool too. Okay, marker. Let me turn the marker off. Now, I do want to draw your attention to one other thing. If we were to zoom out, look what's over here at the very end. Another spike. What? Positive and negative frequencies. You remember how we talked about if you do a cosine, what you should get is two perfect tones like this. One at some positive frequency and one at some negative frequency. Right? So what the FFT has done and this is basically just a byproduct of the way the FFT does the math, is instead of starting at some negative frequency and going to some positive frequency, it starts at 0. It gave you the first peak, this one, and then you got a whole bunch of zeros, and then it almost like wrapped back around to this side, and then gave you this peak over here is the one that corresponds to the negative one. And you can imagine there's almost like a little reflection point in the middle where, so it's like both of them start, it's like you start here, you travel to the right, and then when you get to the end of this axis, it turns around and continues plotting, and then, so this is basically almost 0 again. It's a long story, and it just has to do with the way the FFT math works out. But it's a total pain in the butt, right? Looking at this doesn't help you at all. So we have two problems. One is that we didn't get a frequency vector. The other problem is that our FFT kind of came out backwards, right? We got the positive frequencies, and then we got the negative frequencies, and it's just weird, okay? So it's not hard to fix. It actually has to do with your sampling frequency, which we're going to talk about in a second. So, because I like you, I have made available to you a function that I've written called myFFT. So, this is already on Blackboard. You can download it. Just so you know it's not magic. Here's what you're going to do. So, you're going to pass into it your signal x that you want to take the Fourier transform of, and you're going to pass in the sampling rate of your signal. And I'll tell you what that is in a second. Ignore this stuff right here. That's just some get out of jail free stuff I did in case for some more advanced stuff, but we're not going to use it. Okay. Does that look familiar? Just take the FFT of the signal. I scale it by sampling frequency. Don't worry about that. That's just a divide. Look at what this does. This MATLAB has a built-in function called FFT shift. Guess what FFT shift does? It takes this bit and shifts it over here, so you have something that actually looks normal, right? This is actually a big enough problem that somebody wrote a function for it and stuck it into MATLAB. Okay? I use that function in the myFFT program. So, step 1, take the FFT. Step 2, undo that ridiculous shift that's a byproduct of the FFT. And step 3, look at that. What am I doing in step 3? No. I'm creating a frequency vector for you. You're welcome. Right? That's the missing frequency vector. So there is a way to calculate it, and I don't want you to worry about it. We can talk about it if you care, but I created the frequency vector for you. Okay? So let me show you how to use this. And if you care to talk more about what's under the hood, we can talk about it later. But mostly I just care that you know how to use the tool so that you can do your homework. So let's go back to our little function that we worked out. So instead of using instead of using FFT, we're going to use myFFT. Okay, myFFT takes 2 inputs, the signal that I wish to transform, and the sampling frequency, which I have not yet defined. And it's going to return for me two numbers, 2 arrays. One is capital X, which is the FFT of my signal, and little f, which is the frequency vector. So now when I go to plot this, I can say plot f comma absolute value of x. Now I have something to put on my x-axis that actually is in units of hertz. You're welcome. Okay, so the only missing piece of the puzzle that I need before I can run this is the sampling frequency. Okay, so let me spend about 2 minutes describing what is a sampling frequency. Okay, let's talk about how I define my time vector. You see how I did lin space 0 to 10, 1e5? Okay, so those are evenly spaced points, are they not? Oh, really, black marker? Okay. Okay, so here's my x-axis. So where's my first point on my x-axis? 0. All right, I defined it that way. Where's my second point? What is the value of my second point? I don't know, I could calculate it. I could just come here and say, what is t of 2? Okay, it's about 1 times 10 to the minus 4th.
We do 10 divided by e to the minus 1?
Yes, you could do that. It would basically be the right answer. Okay? And then this would be 2e to the minus 4, and then 3e to the minus 4. So these are all where my times are. Now, the spacing between these points, I could have them, can we agree that I could have more points? I could have more time points. I could have fewer time points. It turns out that spacing between my time points is critical. And that's what's referred to as the sampling frequency. Okay? In 1 second, how many points do I have? Well, look, in 10 seconds, how many points do I have? 1e5. Okay. In 10 seconds, I have 1e5. That means in 1 second, I have 1e4. So in 1 second, I have 1e4 points. That's your sampling rate, F sub s. Sampling frequency. It tells you the number of time points in 1 second. Okay? It tells you number time points per second. So what we're going to do is, now, you can either just eyeball it off of your t definition, or there's a standard way you could do it. You could take the time, you could measure the time between the first 2 points and take the reciprocal of it. That will also give you the sampling frequency. So if we call this the dt, the time between points, the sampling frequency is always the reciprocal of the time between points. So, all I got to do, there's a couple ways of doing this, but basically all I need to do is come here and say, well, my dt, the time between points, is t of 2 minus t of 1. Just let MATLAB figure it out, right? Don't even go to the trouble of eyeballing it. And therefore, fs is the reciprocal of it. And that makes sense, right? If your sampling rate is 1,000 points per second, the time between points is 1 over 1,000. So I'm going to hit run now. And now look at my plot. Well, you can definitely see that I got my little FFT shift action on. Let me zoom in here. Oh, it's looking good. What do you think? Am I showing peaks at plus and minus 1 hertz? Yes. Does that correspond with the sine wave? Yes. Am I seeing other stuff? Yes. We're going to talk about what this other nonsense is. Right? Why is it not a perfect peak? Why is there all this?
It's not a perfect sine wave.
It's a finite cosine.
Right. And we'll talk about that. So can we agree that this is not a perfect sine wave? Perfect sine waves go on for infinity, don't they? Does that one go on for infinity? No, it only goes on for 10 seconds.
But if we're doing the transform, we don't want something that was infinity or we periodic, right?
Right. So here, let me just kind of paint the picture for where we're going with this. Okay, this is totally important. And this is why we talk about, believe it or not, why we're talking about rectangular pulses. Okay? This is not a perfect cosine. And in the real world, there is no such thing as a perfect cosine, right? Every signal has to end. Okay? Nothing goes forever. Well, by truncating it between 0 and 10 seconds, instead of having a pure tone that was exactly at one frequency, multiplied it by a square wave. Hold on to that thought. That's perfect. Instead of getting a perfect tone, you got this other stuff around the perfect tone. And I'm willing to bet you that this shape is not arbitrary. What does that shape kind of look like to you? It looks like a sinc function. Doesn't it? Look like it's got the thing and then the bouncing?
That's basically what we got in computer project 1, right?
Yes. Looks a lot like computer assignment 1. What did you do in computer assignment 1? You multiplied a cosine by a square wave?
Or another period.
Right, but I mean, it's the same general concept. Doesn't it look like a sinc function? That's not an accident. Okay, we're going to put all these pieces together. Okay, it's like a big jigsaw puzzle, and I got to figure out how to get all these pieces onto the board, and then eventually it'll all connect. But your take-home message for today is basically that, first of all, we talked about the square pulses in a bit more detail, and then we started to mess around with how you use the myFFT function to make these plots. And again, it's very easy to use. You just have to know the sampling frequency of your time signal, which ain't hard to calculate. All right? When we come back on Monday, instead of taking the Fourier transform of the cosine, we'll take the Fourier transform of a rectangular pulse, and we'll make sure that what the MATLAB plots for us is exactly the same thing that we got by hand. Yes, sir?
What about the sampling frequency that we get from the wave beam in the sound?
That's built in. So the wave that I gave you.
What I use to plot mine.
Yeah. Well, so when you use the wave read command, the wave read command will tell you not only the actual signal x, but it will also provide for you the sampling frequency.
Shouldn't it be like 44,100 hertz?
Right, and I use the standard audio sampling frequency of 44,100 hertz. So that's your FS that you'll use in the homework assignment. You can't just pick an FS, right? I mean, once the time signal is defined, that's built into the signal. Like the spacing of the time samples defines the sampling frequency. So in the homework assignment, you can't just be like, I want to use 1,000. It doesn't work that way. You've got to use whatever the frequency was that it was sampled at. And in the case of the homework, it was 44,100 hertz. It'll get easier. Okay, I'll see you on Monday.